I'll give an overview and brief demonstration of OPM Flow and also a little bit about ResInsight. So first I'm going to talk about reservoir simulation in general. Then I'm going to show you the mathematical formulation, and some of you might choose to turn on your screensavers at that point. I hope to carry the rest of you through. Then I'll discuss how we have implemented this using automatic differentiation, and then a brief what's next. I wouldn't call that an overview. It's more like some of the things we are thinking of doing. I don't even mention the chemical things there, for example, but it certainly has been thought of and is still thought of. So reservoir simulation is to simulate flow in a porous medium in subsurface reservoirs. And the reservoirs being subsurface means that you usually don't have a really good idea about its properties. You may have seismic surveys, you may have well logs and so on, but you cannot take it up, look at it, that's the way it is. That's just impossible. So, so you're starting from a quite limited set of information. And creating just the simulation grid, creating the simulation case is a major undertaking in itself, which I'm not going to say much more about because this is about reservoir simulation, which is what happens after you have created the simulation case and you want to get the results. So important examples of use are in the energy industry for forecasting and optimizing production of oil, gas, and also geothermal energy. And groundwater flows and pollutants are also an important use case for reservoir simulation. And CO2 storage, CO2 sequestration has become important in the last, say, 10 years to study, to look at how is it safe, is it effective. So, reservoir simulators solve systems of nonlinear partial differential equations that are coupled to well or facility models. So that's the basic mathematical approach. So why is this hard? First of all, the porous medium is strongly heterogeneous and anisotropic. Which means that, as a consequence, cells are usually don't have nice shapes. They usually have large aspect ratios. Typical cell might be 50 by 50 by 2 meters, or well, plus minus a lot. But they typically have quite high anisotropic ratios, and also anisotropic and heterogeneous effective properties like permeability. Oh, I already said this, and I also already mentioned that the grids are usually fully unstructured due to the faults, especially. And phase here I'm saying non-trivial phase behavior is non-trivial, yes, and it's also a part of this. Phases can appear and disappear. For example, the light hydrocarbons can dissolve into an oil phase, so then the gas phase disappears, and then the pressure drops for some reason, and then below the so-called bubble point, and then the gas will come out of the solution again as the solution becomes saturated with the gas, and you'll have a free gas phase again. So that's part of what makes it difficult. So, and well coupling can connect regions that are far away from each other. And also the models are usually highly nonlinear. So this is an example of another of this bad grid. This is a candidate for the worst looking. Although it's actually very nice because it's in a shoebox shape, so it's not that bad. But its interior consists of really undulating surfaces that make any reasonable discretization not like this grid. So you have to use unreasonable discretizations, actually. And this is just the same case you saw before, the Nune grid. I think it also shows the wells, but they are, or some wells at least, but they are very, they're not very visible, but you can see here's a well, here's a well, here's a well, here's a well, here's a well. And these are just points where the wells come up out of the reservoir. Down in the reservoir, they have actually a shape like this. So why does this require HPC or cloud computing? One thing is that model sizes are increasing. Saudi Aramco recently set a new record by with their so-called powers reservoir simulation software. They now call it, they used to call it gigapowers for a while, since they had simulated on 1 billion cells, and now they have simulated on 1 trillion cells, so they call it terapowers now. So on one hand, these are just bragging points, but on the other hand, it's really shows that some actors in this field are really pursuing the extreme scale in terms of simulation grids. We are at the other end, to put it like that. We're not really pursuing this, not at the moment, eventually, maybe. So model complexity is increasing. We are looking at more complex well and facility models and more complex fluid models. There are new mechanisms that are becoming important, such as injection of polymer, injection of CO2. These mechanisms, many of them, require a better resolved fronts. Fluid fronts are often self-sharpening in some cases. But for these cases, the fronts are no longer self-sharpening, so you need to have a finer resolution, either using higher order methods or using higher grid resolution to get them resolved. And we want to do large ensembles for history matching, optimization, and uncertainty quantification. So the market situation, I'll say a little bit about that. So there are commercial reservoir simulators, which are expensive, but they are in general quite good at what they do. So Eclipse has been the most popular reservoir simulator for many years. And you might say it's the industry standard. So the input and output formats that we support are basically compatible with Eclipse input and output formats, because it gives the lowest barrier for existing users of reservoir simulation software to use OPM. There are many more. Intersect is Schlumberger's latest reservoir simulator. They try to get people to replace Eclipse with Intersect. They're not succeeding 100% in that, because Eclipse still is very popular. Computer Modeling Group is another actor in this field. They have some highly regarded simulators. There's a Russian company that has a product called T-Navigator. There are many more. Each of these have their own special features or things they are particularly good at to attract customers. Then there are lots of in-house simulators. That's gigapowers. Oh, I should say terapowers now. Sorry for this. I forgot about that. There's like more. Shell has its own. Many more oil companies have their own in-house simulators and do not use the commercial ones as their primary simulators. There are Stanford University has a general purpose reservoir simulator, GPRS. But in general, all of these in-house simulators are not available to outsiders. So some are available to researchers if you manage to become an insider in some way, join a consortium or something. But they are not open source. They are not sold commercially. They are usually simply not available to most people. So then there are open source simulators. There are essentially only two. There's OPM Flow, and there's the MATLAB Reservoir Simulation Toolbox, which is also created by the group I'm in at SINTEF. The difference, one difference is that MRST is written in MATLAB, so it's slower, but it's also slightly easier to use as a prototyping tool if you're familiar with MATLAB, whereas OPM Flow is written in C++, and it's designed to be, or intended to be fast, and you don't need MATLAB to run it. So OPM Flow at a glance. This slide is, I think, quite similar to one you saw yesterday. So I'll just sum it up. It's studied open source. We handle cases of full industrial complexity with competitive performance relative to the commercial and other solvers. And it's currently used for oil production studies, enhanced oil recovery, and CO2 sequestration studies. So, and it's implemented using automatic differentiation to have rapid development of fluid models. I'll say a little bit more, quite a bit more about that later, actually. So now the mathematical formulation. So first, what are the basic physical laws and behaviors that are important? Conservation of mass, of course, for each fluid pseudo-component, oil, gas, and water. And we conserve the mass of injected EOR fluids, for example, in extended models, for example, polymer, CO2, or surfactants. And the geochemical question here, conservation for ion species, I put it in parentheses because we don't support it, but we want to. And it would belong here. You would need to conserve the mass of each ion. And this is the basic mathematical formula. It's just conservation of porosity times an accumulation term plus the divergence of the velocity of that component equals some source term. So it's very simple when you write it down like that. So then there's Darcy's law. For a single phase flow, Darcy's law says that the velocity in a porous medium of a fluid is proportional to the gradient of the pressure. And we have to include the gravity, so it's the gradient of a potential. And then the K here is a permeability. So the permeability is a proportionality constant between the pressure gradient and the flow velocity. And then you divide by the viscosity of the fluid. So far, so good. This is not a law that has been derived originally from first principles, but actually from it's an experimental law. So Darcy made experiments and derived this law many years ago. For multi-phase flow, we have the concepts of relative permeability and capillary pressure. First of all, the flow rate is reduced due to the presence of other phases. So the flow rate of one phase is reduced because the other phases take up room in the pores. So there's less room for this for one phase to move. So this is reflected by Kr, the relative permeability, which is a function of fluid saturations. So this enters the equation here. Instead of the 1, you have the Kr. So the pressure differences between phases is also a thing that's due to the capillary pressure. So you have to do pressure by phase and not one universal pressure for all phases. So the black oil model is what Flow implements. There are some assumptions here. We lump all the hydrocarbon species into two pseudo-components, oil and gas. So basically, all the light components are gas and all the heavy components are oil. And then we allow the oleic phase to contain both oil and gas components. So, and we give a ratio here for how much dissolved gas is there in the oleic phase. And we allow the gaseous phase to contain both oil and gas components as well, where there's a corresponding vaporized oil ratio, RV, which says how much oil has vaporized into this gaseous phase. And it's assumed to always be at thermodynamic equilibrium, so there are no transient effects in transitioning between the states here. And the assumption is also that the PVT relations are simple enough that you can just use a simple table lookup to get your densities, viscosities, etc. Usually a 2D table lookup, but still quite simple nonetheless. So some consequences are, first of all, people always confuse the oil phase and the oil component. So this is very easy to confuse because usually we talk about the three phases, water, oil, gas, and the three components, water, oil, gas. But the components can be water. The oil and gas component can be in either the oil phase or the gas phase or in both. So properly should gaseous phase, oleic phase, but in practice people forget that. So, and I will too once this slide has become the previous slide. I will also forget it, and I'll talk about the gas phase and the oil phase, even though and not make a very clear distinction between them, only when I want to point out actually the difference. Another consequence is that you have three different types of states in any point. At any point, you can have a fully saturated state when all three phases are present. You can have an undersaturated oil state when there's no gaseous state. All the gas has been has dissolved into the oil phase and is still undersaturated, because when it gets saturated, then the excess gas has to go into its own phase. And there's an undersaturated gas possibility, which is just vice versa. All the oil has vaporized into the gas phase. So, and this is a subset of a more general so-called compositional model, where you can't, in general, look up in a table based on RS, RV, and pressure to find your densities and your viscosities, but you must solve an equation of state, such as Pang-Robinson. I put this in parentheses because that's something we don't currently support in Flow. So here's then the system of equations. So for each pseudo component alpha, we have this conservation equation. And I'm just writing out a few things here. Just note that the u here is the velocity of a component, the flux of a component. So v, on the other hand, is the flux of a phase. So this is like a mass flux of a component. This is like a volume flux of a phase. So converting for the water is just it's simple. It's just a proportionality. But the flux of oil it takes into account oil in the oil phase and oil in the gaseous phase. And the gas velocity, gas component velocity, takes into account gas in the gaseous phase and gas in the oleic phase. So that's part of the complexity here. And also these B factors, they are called inverse formation volume factors in oil speak, which they basically behave like densities. Think of them like densities. So and they depend on pressure and on these dissolution factors and so on. So that's part of where the nonlinearity comes in. So also we want saturations to sum to 1, basically saying that our fluids fill the available pore volume. And there are capillary pressure relations. Basically, these things here are going to be functions of saturations. So that's another source of nonlinearity. And finally, Darcy's law by phase, as you saw on the previous slide. So what is this source term? I didn't say much about that. Those are well rates, usually. So you will couple your reservoir model to a well model. And the well models can be quite complicated or they can be quite simple. But usually they have their own unknowns, or at least one unknown, but often more. And, oops. And they must be usually solved simultaneously with the reservoir equations. So this is another source of complexity. So these systems are discretized usually using first order implicit Euler in time, first order finite volumes in space, using the so-called 2-point flux approximation. Now this, you remember I said that for reasonable grids you can use reasonable discretizations, but for unreasonable grids you have to use unreasonable discretizations. This is an unreasonable discretization. It's consistent only for particular types of grid, but it's robust and works and give you an answer on arbitrary kinds of grids. which is why it's popular. So it's more important to get an answer than to get one you know is right, in some sense. It's of course that's putting a slightly too mathematical spin on it. But in some sense, this is usually not strictly correct from a mathematical point of view, but still it works well enough. So, oops. Another thing, point about discretization is that we use phase-based upwinding of properties. This is rather common in hyperbolic equation solving. So, and why do we use these primitive methods of low order and sometimes even inconsistent? Well, historically, these things were solved with finite difference methods, and doing higher order finite difference methods is not something I would like to do. At least it's hard, and we need systems that linear solvers can deal with well, and they deal fairly well with these systems. It's already quite complicated to solve these nonlinear systems, but with higher order, it becomes even harder. And it's sufficient for practical purposes. The engineering golden rule: if it works, why change it? And discretization errors are often not significant compared to the inherent uncertainty given by you don't know the domain. You don't really know it. You have some idea about the properties, but you don't really know them to any precise degree. So, but quite a bit has been done. On consistent discretizations, there's something called the multi-point flux approximation and mimetic methods. And for the upscaling part, we use mimetic methods. For OPM Flow, we use a 2-point flux approximation, the simpler one. Work has been done on higher order finite volume or discontinuous Galerkin methods and higher order time discretizations, but none of this is mainstream yet. But I'm saying, if and when it becomes mainstream, I'd like it to become mainstream through OPM Flow and not through someone else's software. And I think it's much more likely that it will happen in Flow than in some commercial software. So the discretized equations, they are superficially quite similar to the continuous one I just gave earlier. So basically, you have accumulation terms, this is first order Euler discretization, and then you just have a discrete divergence term here and a discrete source term coming from the wells. And these discrete relations look very much like the continuous ones. But the fluxes for each connection ij between cells I and cell j are given by using something called Tij here, which is the transmissibility. So this is the 2-point flux approximation. It basically says that the flux between two points is given by the difference in some potential times the transmissibility. So I'll skip this. I put it mostly in this to be as a reference if you're curious later. So then we solve the discrete equations. And for that we use Newton-Raphson. We need to solve large heterogeneous linear systems. These systems have unknowns of different types. You will have typically a pressure unknown and 1 or 2 saturation unknowns. So you have unknowns of different types, equations of different type, and you put all this in a single linear system. It's a challenging thing to solve. So it's challenging to precondition it. Some people claim that combination of CPR, which is a special method for these problems, with an algebraic multigrid method is the best, but jury is still out. Our default method is ILU 0 in a block way with this a block of equations and unknowns for each cell. You must modify the update to account for the phase changes. You must, when you change, a cell goes from containing no gas to containing gas, you have to be careful not to overstep too much and get into an oscillatory regime where it switches between gas, no gas, gas, no gas, and with no end in sight. And you will have convergence failures, so you need to handle that somehow, and the usual way is to then to cut the time step until it converges. So that happens fairly often. So I'll see, how much time do I have for this part? Not much at all. I'll say, what does automatic differentiation provide? The traditional process is that a human needs to implement the function, the residual function, and then the Jacobian, we can use do it on paper or use some other system to find the derivative, the Jacobian, and then we implement code for this and we implement code for this from these equations. And for these rather complex nonlinear equations, writing out the Jacobian can take pages of a research article. So it's really nasty and very easy to make a mistake, either in the symbolic derivation or in the implementation, especially in the implementation. So with AD, you implement code for the residual, but then you get the derivative, the Jacobian, for free. It's automatically generated. So this makes it easier to create simulators because you only specify the nonlinear residual and you automatically get the Jacobians. And you can also automatically get the sparsity structure of the Jacobians depending on the type of AD you're using. It's not the same as finite differencing. You don't need to define an epsilon or something. You get the same precision as a handmade Jacobian, but with much less work. So performance of this, actually computing Jacobian, will usually be a little bit slower than a good handmade Jacobian implementation. Our first experiments with this, we discovered that our handmade Jacobian implementation was bad because the first time we made an experiment with it, the new code using AD was twice as fast at the assembly part. So if you're very sure that you have an excellent, optimized, handmade Jacobian implementation, then don't use AD, unless you want to change it. Then you would be happy to use AD anyway. So the basic idea is to write a numerical computation as what's the term? When you evaluate one function inside the other, there's composition, thank you, of simple functions. So, this is the final, you want y equal to fn of yn plus 1, n minus 1, and then all the way down to yn equals f1 of x. So, and then the derivative, you get that simply by the chain rule. And there are two main methods. Use operator overloading, this is what we do, and the other one is to have an automatic differentiation tool that does source transformation. Source transformation requires you to stay within a subset of the programming language you're in so that the tool can understand what you're doing and make the code for the derivative automatically. Operator overloading is easier to use but requires a host language that supports it, such as C++. So, and then there are two types of AD. There's a forward mode where you carry on with your derivatives with respect to independent variables. So your objects would, instead of being just a value u, it would be u and the derivative u with respect to x. And the reverse mode, you carry derivatives with respect to the dependent variables, so it would be adjoints. And yeah, I'll skip through this example. You can look at it afterwards. And the reverse AD example. And finally, a few notes about the implementations in OPM. We have a legacy implementation doing this in a vectorized fashion, and a new effort which does it single scalar value at a time. It's a simpler code in itself, and we do this because it turned out this gave much better cache performance, so it was more efficient. So we switched to that one. Okay, we keep pursuing performance, and we're looking at improving preconditioners and linear solvers. new discretizations, nonlinear preconditioning, parallel scaling. We're trying to improve usability all the time. Work has been started on a reference manual. We are getting more output or logging options and better error messages. Slowly but surely, error messages are becoming possible to read by engineers and not just the coder who wrote it. And deployability. Through container usage, we support Docker right now. Through the MSO for SC Portable and web integration. And this should have been deleted. So further ahead, these are some of the possibilities. New fluid models, make it scriptable, more flexible boundary conditions. That's in particular important for groundwater pollution type cases. Not so important for petroleum. Higher order DG methods, consistent discretizations, fully compositional fluid model, new I/O system for parallel scalability. Our I/O is currently serial, which is not a big problem as long as you are on, let's say, a single workstation, or up to, I'd say up to 12 or 16 nodes. This has so far not been the big bottleneck, but it will be eventually. And what about pre-processing tools for creating these models, going one step upstream from where we are now? These are just ideas. So thanks for listening. I'll have a little bit of time for a demonstration, but actually I don't. Do I? I used up all the time.
How much time?
But
How much time do you need?
okay. Yeah. Okay. So this is I'm logged into the Seska system. So I'll and it has installed. It has installed the simulator Flow. So now I just started a job running a rather simple test case. And Victor, you remind me, what command do I use to see if it's running, or? SQ? Like that? What is QU, like that? Oh yeah, this way. Yeah. Oh yeah, it's this means it's still running, right? Yeah. And now it was done. Okay. So I'll.
Excuse me, can you make the font bigger, please?
Oh, maybe I'll try. That's not bigger. That's smaller. Oh yeah. Okay. Well, I'll switch to this one anyway. Done with that demo. Too late to make it.
Okay.
So, and then I'll just show you the results of this run in the ResinSight software. So this case is it's a very simple small case. So how do I? So this case is a reservoir with you can see there's a water layer at the bottom, and then there's a transition to oil, and then an oil zone. And at this point, I lost my. Oh yeah, there it is. And you can see that as time goes on, well, something should happen here. Yeah, you see that the oil gets depleted by the production wells, which are all these wells here, and there's a single injection well there. But what I really wanted to show you was the gas phase. So at the start, there's no free gas. But as we start producing, the pressure drops below the bubble point, and free gas comes out of the solution. So there comes a free gas phase here. So just with that, I think I have to stop. And thank you very much.
Thank you, Atgeirr.